So the second approach is that we'll be using a wait for graph to detect deadlock. If so, we allow the transactions to run concurrently, check whether a deadlock exists using a wait for graph, right? So only if a deadlock exists, then we'll be suspending some transactions, or we'll be terminating some transactions to recover from the deadlock, right? So how to detect a deadlock in a set of transactions? So for deadlock detection, we have this wait for graph. So deadlock can be described precisely in terms of a directed graph called a wait for graph, right? So any graph is described by a set of vertices and edges, right? So here the set of vertices consists of all the transactions in the system, right? So here if a transaction is waiting for a data item that is being held by some other transaction, then we say that there exists an edge between transaction T1 and T2, right? So each element in the set E of edges is an ordered pair Ti to Tj. So if there is a directed edge from transaction Ti to Tj, it implies that transaction Ti is waiting for the transaction Tj to release a data item that it needs, right? So we are going to represent uh, deadlock detection by means of a wait for graph, where nodes represents the transaction and edges, they represent the relationship between the transactions. So if there exists an edge between transaction Ti and Tj, it implies that transaction Ti is waiting for the data item that is being held by transaction Tj, right? So a deadlock exists in the system only if the wait for graph contains a cycle, right? So you're going to represent the information in the form of an wait for graph, and if the wait for graph represents a cycle, we say that the transaction is deadlocked. Else we say that all the transactions can proceed without any conflicts, right? So for example, to illustrate this concept, we are going to have this figure 15.13, which represents a wait for graph with no cycle, right? So here transaction T7, so here we have four transactions, T7, T18, T19 and T20. So this graph implies that transaction T7 is waiting for the data item that is being held by transaction T18 and transaction T19, and transaction T18 is waiting for the data item that is being held by transaction T20, and transaction T19 is waiting for the data item that is being held by transaction T18, right? So since the wait for graph has no cycle, the system is not in a deadlock state, right? So this is an example for a wait for graph where there is no deadlock state, whereas this wait for graph, there is a cyclic graph, right? So it means that the transactions are in a deadlock state, right? So you are going to add a edge link between transaction T19 to T20, right? Sorry, T20 to T19 is added to a wait for graph, resulting in the new system state like this figure 15.14, right? So initially we don't have cycle in a wait for graph. Now we are going to introduce a cycle by having an edge, directed edge between transaction T20 and T19. So we have a cyclic format in the wait for graph, right? So now we say that since the graph contains a cycle, we say that the transactions are deadlocked, right? So by using this wait for graph, you'll be able to detect whether deadlock exists among the transactions, concurrently executing transactions, right? So once you find the graph is going to be cyclic, wait for graph is cyclic, it means that the transactions in